We're going to jump right back into it to talk about surface power. Surface power sparks lunar exploration. This session is once again brought to you by our all-day sponsor, BWX Technologies, as well as Aerojet Rocketdyne. So let's welcome our moderator, Lisa May, the Deep Exploration Strategy and Business Development Lead at Lockheed Martin. Lisa is an accomplished senior executive, entrepreneur, program manager, and systems engineer with more than 35 years of success in aerospace and technology. She has led NASA and industry teams in the exploration of the solar system, Mars sample return, and enabling human exploration. Lisa specializes in assuring strategy investments and implementation align with customer and market priorities, and execution supports the highest level objectives. Also, Lisa was elected an AAS Fellow in 2021. So with that, I turn it over to Lisa.
Of the future lunar economy, and I have a terrific panel for you today of experts from industry and NASA, and without further ado, I am going to start off with Dr. Lindsay Caldone, who is the Fission Surface Power Project Manager at NASA's Glenn Research Center in some place called Cleveland. She, having lived in Maryland like you did, I sympathize with having recently relocated. She most recently was working for the Department of the Navy in NAVSEA Systems Command, where she was the technical lead and deputy program manager within the electromagnetic pulse group for Navy surface ships. Before that, she's worked on robotic intelligence aircraft for both the Navy and the Air Force, and began her professional career as an active duty Air Force electronic warfare officer on both high altitude U-2 and Global Hawk aircraft, which actually it was over Global Hawk I met John Tilko, who was here earlier. So it's a very small community, and we will all come back around. Lindsay has a bachelor's degree in electrical engineering from the University of Evansville, a professional degree in systems engineering from the Naval Postgraduate School, and a master's degree in nuclear engineering from Penn State, where she focused on radioisotope power and nuclear propulsion systems, which is very relevant to your current position and to why we're here on this panel. She also has a private pilot's license with instrument rating and loves to go flying. So without further ado, on to you.
Okay. Okay, good morning. As Lisa said, I'm the Fission Surface Power Project Manager at NASA Glenn, and I will be providing an overview of that project as well as touching on NASA's power infrastructure in general. So what is the motivation behind surface power? I'm not just talking nuclear, I'm talking surface power as a whole. Is something called Moon to Mars, and you might have heard of this. The current scope is to establish a human presence on the moon, and you can think of that kind of as practice for Mars in the future. In April, this development, this blueprint was released by NASA, NASA headquarters, and there are various goals listed here. The human lunar return, foundational exploration, sustained lunar evolution, and humans to Mars. And this infrastructure is really laid out to discuss, sustained lunar economy, going along in parallel with the exploration of Mars. And what's interesting is that the two top objectives for lunar infrastructure and for Mars infrastructure are to establish a power presence on these celestial bodies. And as far as why we need surface power, ISRU is king. That is the key driver, in situ resource utilization. And I think, I've got these 4 quads listed here. It reminds me of a game called SimCity. I don't know if y'all had ever played that, where you build your grid, you put your buildings on. And I remember when I first played it, I would put my city together, and it was like nothing happened. And it wasn't until you popped that power in is when the magic happened. It's when everything started to come alive. And you can kind of think of it, with surface power the same way here. We can have buildings, we can have habitats and everything else on the moon, but it's not until you have that power in place that really things start to happen. And so for ISRU, these are the different elements that are going to require a surface power presence, is to use it as a resource mining. So you've got the first quad there, commercial scale water, oxygen, metals, and commodity production. You can also, you need power to end up with a way to grow food for the habitats. As far as looking further down the road, maybe we can start building things. Maybe we can print things there on the moon. So you need the power to be able to do that. And then commodities for commercial reusability and space and surface transportation and depots. So yesterday I had a really great conversation with NASA headquarters principal technologist for power and energy storage. And I said, what is our plans long-term for lunar power infrastructure? And this is the chart that he provided me. There were really kind of 3 phases here. And you notice on this chart on the left side, the scale there, that's logarithmic scale with your power levels, and then the X scale is your distance. And so we start off small. When we get to the moon, you can see the Artemis base camp. That's there, the little pink box. And that's essentially the mission there is for foundational exploration and practice for those humans going to Mars. But you can see the power levels are quite low. The distances are quite small. However, we hope to be able to use lessons learned from that to get to a phase alpha. This is where you've got some of that ISRU stuff really picking up. And NASA could be one customer. We really kind of envision, industry coming in and kind of setting up a presence there. And then much further long term, you've got your phase Omega, which is going to be your large global industrial grids. And that's some of the images there up on the upper right-hand corner in yellow. But what I want to point out is if you look down at the bottom of the slide, under Artemis Base Camp to the left, there are these little images. They're kind of like little army men. You can move around. But the one on the left, that is fission surface power. You've got vertical photovoltaic systems. You have a ISRU pilot plant, and various other power sources that we envision is going to be needed for the lunar infrastructure. And I myself am partial to the one on the far left. That is fission surface power. And I'm going to give a few slides on that. When I was working in the Department of Defense, every now and then you end up with a technology that they call a key enabler. And before I left there, it was hypersonics. Like that is going to be a game changer in the military. And I kind of see fission surface power being that key enabler for lunar and Mars infrastructure for the power subarchitecture. Why fission surface power? Well, nuclear power systems, they give you an option, where you may not have that option with solar or with wind, energy production methods. If you were on the moon, we could end up in a permanently shadowed crater. So the solar option may not be there for where we place this system. And so nuclear, you don't need that reliance. The wind, we don't have wind on the moon, so that's not really an option. Looking forward to Mars, you have these really awful encompassing dust storms. And so fission surface power is really that key enabler to allow the successful exploration of the moon and Mars. Fission surface power, just a brief overview of some of the very top level goals that we're working towards right now is a 40 kilowatt electric reactor having an autonomous lifetime of 10 years, where you're not able to, you don't have to go and refuel it, you don't have to do much of anything to it. So this is going to be a fun project to really work out those requirements to make sure that it is sustainable and reliable. And then a mass of less than 6 metric tons. We do need to make sure we make it as light as we can to get it up there in space. And one other key design attribute is that we're using HALEU, high assay low enriched uranium, as opposed to systems in the past, because fission surface power is not new to NASA. We've been working on fission reactors since the 60s, with SNAP-10 back in the 60s, to Prometheus, we had an FSP 1.0 about 10 years ago or so, and then Kilopower, Krusty, which was a 1 kilowatt system. Those all used highly enriched uranium. Now, because of SPD 20, we're directed to look at a lower enriched uranium HALEU, and that's requiring some design changes. But I think overall it's going to be it's for anti-proliferation concerns, it's probably the way to go. Okay, and as far as our development strategy goes, back in 2022, we awarded 3 FSP design contracts to industry, and those 3 partnerships are shown here: Lockheed Martin with BWXT, Westinghouse with Aerojet Rocketdyne, and Intuitive Machines with X Energy. And these are a way for NASA, in conjunction with DOE, Idaho National Lab is who's actually managing the contract for that. We are able to get really innovative ideas from the 3 partnerships. We didn't levy a whole lot of requirements on them, which has its pros and cons, but overall I think we're able to kind of see some of that out-of-the-box thinking, to recognize they're bringing forth some really neat ideas, and we're also able to find some areas that could be a challenge or a risk going in the future. So we consider this period right now phase 1. FSP is in pre-formulation phase, where we are doing concept designs. After this phase is over, we plan to release an RFP out to industry. This will be the design contract that will deliver a qualification unit, a flight unit. But for now, we are just looking at these designs and making sure we have the requirements that we need to go forth with that RFP. We're not going to let the partnerships have all the fun. We are doing government reference design as well at NASA Glenn in conjunction with DOE. We work closely with Los Alamos National Lab on our reactor research. The non-nuclear aspects, Glenn has a very rich history of, you can consider it a center of excellence for power conversion systems, for things like integrated heat pipes. And I do want to point out here, we do have a solicitation out on the streets on NSPIRES right now for a high temperature Brayton procurement effort. So I think that runs until the 7th of August. So we are actively doing technology maturation, both on the nuclear and non-nuclear sides. We do want to make sure we are engaged fully with industry as we're working through this. And so we offer these webinars, and the next one I've highlighted in blue will be on July 26th, and that is open to anybody that would like to hear the latest in our design efforts. All right. And just in summary, again, we're working closely with the Department of Energy and their laboratories to come up with a fission surface power system that can meet that Moon to Mars goal. And I mentioned the technology investments that we're working on, the nuclear and the non-nuclear side. And I think really the key to the success of this effort, to be able to do the Moon to Mars, is to have that engagement with industry, with academia, with all of you, as we move forward to build this reactor system. Thank you.
Thank you, Lindsay. All right, our next presenter is Vince Bellardo, who's the co-founder of Bellardo Associates, which is a consulting firm. He has 40 years of experience as an expert program and project manager, as well as systems engineer in the aerospace and defense industry. He has direct experience in nuclear space. He was the deputy program manager on he is currently serving as the deputy program manager on the IX, Intuitive Machines X Energy Fission Surface Power Study. Previously, he was here at Glenn Research Center. He directed the Advanced Stirling Radioisotope Generator Program, ASRG, for those here who have experience with that, for deep space science missions while serving on a detail assignment to DOE's Office of Nuclear Energy. Prior to founding Bellardo Associates, he also directed the power and propulsion element for the Deep Space Gateway while at Maxar Space. Vince has a Program Management Professional Certificate from the Project Management Professional Certificate from the Project Management Institute, as well as BS and Master's degrees in Mechanical Engineering right here, Case Western Reserve University. So Vince, all yours.
Very good, Lisa. Thank you. Good morning, everyone. So just a quick disclaimer before I get into the charts. Even though I am serving on the Intuitive Machines X Energy Phase 1 Fission Surface Power Study Team, my remarks here today are primarily my own, working as a consultant in the nuclear space industry today. And so towards that end, I want to talk about not only where we are today, but where we're going forward in the future in fission surface power specifically, and nuclear space in general. And to do that, right, we're all interested in, okay, kind of what comes next. We've got a lot of momentum right now in nuclear space across NASA, Department of Energy, and multiple DoD agencies. So there's a lot of interest in nuclear space, not just for fission surface power, but also, of course, nuclear thermal propulsion, and looking forward to nuclear electric propulsion, which is kind of a close sister to the fission surface power relative to the reactor solution and the power conversion solutions specifically. But in looking across that spectrum, you also have to factor in political realities. And so what is the current context of where we find ourselves here in mid-2023? Well, first of all, we know we now have divided government with the House controlled by the Republicans, the Senate by the Democrats, and Democrats holding the White House, of course. So anytime you get into divided government, you've got to govern around compromise. And so you're seeing that happening now in the current U.S. political context. But what's happening next year, how could we forget, right? Because we're hearing about it every day on the news, and that, of course, is the next presidential election, 2024. So you've got at least 2 fiscal years of authorization and appropriations in front of us here, FY24 coming up, and then FY25, where it's going to be potentially very difficult for NASA to secure a program new start for Phase 2 fission surface power, what could ultimately be a $1 billion program, billion with a B, over 4, 6, 8 years. So given that reality, together with also all of the mouths at the trough, if you will, in terms of the Artemis enterprise, you saw all of those different elements on AC's chart during the keynote presentation yesterday. There's a lot of hardware elements and systems that need to be put down on the surface of the moon in order to enable the Artemis enterprise, in order to get to that base camp that Lindsay showed on her chart. You need something for the astronauts to do other than drive around in a rover for a couple weeks and get back in the lander and go back home. We want to go to stay this time. So there's a lot of competing priorities across the NASA programs for the NASA budget. And so in that current environment, my take on that is that it's going to be a challenge for NASA to secure formal New START project authorizations for these different Artemis elements. And of course, there's got to be a priority in which NASA brings those forward to Congress to ask for the formal New START authorities. And we now have the architecture that's been rolled out earlier this year. So we kind of know what all the pieces parts are. And now it's a question of in what order do we try to get those funded and developed, and in what order, what priority do we need? We know that power is key, right? Every system that flies in space has to have sufficient power, or you can't really get up there and do anything. You can't even launch and operate the vehicle or the mission. So we know power is key. We know we're in a tough political environment. How do we continue to build on the momentum that we have in the nuclear space arena that we've seen emerge over the last 2, 3, 4 years? So a couple of thoughts on strategy here in response to that. First of all, adopt a program model of development through multiple phases of work. So let's try to eat the enchilada one bite at a time. Literally, I'm a big fan of Mexican food, so I like that one better than eating the elephant. I'd never figured out how you could eat an elephant. But do this in multiple phases of work that are maybe smaller budgetarily, easier to justify, easier to win and program, and get contracts in place, or in the case of the fission surface power phase 1 contracts, find a way to extend those, continue them, so as to continue the momentum and not have a downtime, a period where there's a gap in coverage that causes us on the industry side to have to reassign our teams. And so this is a real thing when you're working in industry. You've got to keep your people employed gainfully on the programs of record. And if there's a lull in there, you can't just let those people sit back and read the paper and drink coffee all day, right? They're engineers. You got to put them to work. So that's a key from the industry side, is how do we keep the momentum going so we can keep the teams that we've worked hard to put in place and gotten them up to speed continuing to work. And then thirdly, studies are great, and we've all worked on studies for years. We kind of know what these systems need to look like right now, and we kind of know what the list of enabling technologies is. But can we now begin to pivot over from study phase into investing in those technologies? And so that's kind of my third thought on strategy here. Through the studies, and this is in my career at least the third wave of interest and investment in nuclear space, and there's at least one before that, before my career started, and that was of course flying the reactor in 1965, the only U.S. fission-based reactor that's ever flown. So we've seen waves of interest followed by disinterest, disinvestment. We're currently in a strong wave of interest and investment, and it's now time to move the ball down the field in terms of these enabling technologies. These are the same technologies that we studied during Prometheus in 2005, the same ones that we studied during FSP 1.0 in the 2010 timeframe. And they're the same because the physics of the problem hasn't changed in the last 60 years. So start with the fission reactor. There are a whole bunch of things going on inside a fission reactor that need to be matured, that are sitting at a TRL around 3 today. We're talking about fuel types and forms. Lindsay mentioned that we're pivoting over from HEU, highly enriched uranium, to HALEU, high assay low enriched uranium. That's a policy-driven decision, not necessarily a scientifically or engineering-driven decision. Okay, it's made, it's written up in policy, we need to live with that now. So what do? We need to find fuel types and forms that we can manufacture the HALEU sustainably in. We have to go qualify those across the entire spectrum of the environments that they're going to see. There are moderators that have to be, these are what we call moderated fission reactors. So you're trying to slow down the neutrons, keep them in the fuel, bouncing around and generating sustainable heat. So there are moderator systems that have to be developed that are the same kind of material problem as the fuel types. And then there's cladding materials, so you keep the hydrogen inside the fuel and the moderator elements, not let that hydrogen escape. That is the type of work at small scale, at fuel compact scale, that we can get started on today. Next is power conversion. Fundamentally, the fission reactor is a heat generation source. So now you're trying to take that heat and convert it into electricity. We have systems that for doing that power conversion that are well known, that are based on thermodynamics that go back almost 3 centuries now. The Stirling and the Brayton cycle being the two that we think are the most practical and feasible for converting the reactor heat into electricity to feed into the power management distribution subsystem. So I'm advocating here that the government invest in a parallel track, not try to down select to one of these prematurely, but continue to invest both in Stirling at the 6 kilowatt engine scale, as well as in Brayton converters, anywhere from 10 up to 25 kilowatt at the Brayton unit level. Keep both of those investments going in parallel right now. It's too early to try to down select. Thirdly, radiation. Radiation is a key problem with the fission surface power architecture, really with any nuclear space system, protecting both the humans that would interact or be operating, let's say, within a 1 kilometer or plus radius around the fission surface power system, as well as the avionics. We need to develop hardened avionics. You saw this also on Lindsay's chart as an area of current government investment, where we are hardening instrumentation, controls, computer chips, both for the space environment, which we're used to. We have hardened EEE parts for flying in space, but now overlaying on the Venn diagram the fission, neutron, and gamma environment that these systems are going to see proximate to the reactor. And then finally, radiators. We know how to fly radiators. We've flown those in space a lot before, but these need to be very large systems, durable. They need to be lightweight. They can be fragile. So let's not think that just the heat rejection part is already solved. There is some technology development and engineering advanced development that is still needed on the heat rejection side. So that's the set of enabling technologies that need to be matured. In closing, let's find a way to start to move some investment into the tech mat so that we can move the ball down the field and build on the progress that we can make year over year, while we advocate for the big phase 2 new start. Thank you.
Thanks, Vince. All right, our final presenter of the morning is Navid Fatemi, who's Vice President of Business Development at Solero by Rocket Lab. That's quite a name, Solero by Rocket Lab. I feel like I'm on NPR suddenly. Mr. Fatemi joined Solero by Rocket Lab in 1998 and oversees business development, sales, marketing, and proposal management for the company. He has 30 years of experience in aerospace and photovoltaic industries, and prior to joining Solero by Rocket Lab, he was a partner at Essential Research Incorporated in Cleveland here, and was involved with photovoltaic research and development activities for space applications at NASA Glenn. Mr. Fatemi has a bachelor's and a master's in electrical engineering, one from Case Western and the other from Cleveland State. So, over to you, Navid.
Thanks, Lisa. I appreciate it. Good morning. So, I'm the one of obviously representing industry here, purely commercial company. So I'm going to talk a little bit about who Rocket Lab is and what they do. Rocket Lab, you may be familiar with the name. It's many people consider it to be like a very small version of SpaceX, purely commercial, founded in 2006, essentially delivering rockets to space, building and flying them. And notably, the rocket that we currently have is called Electron. It's a small rocket. And last night had its 39th successful launch, deploying 7 separate satellites, most of them for NASA and others. So Rocket Lab actually has 2 separate divisions. The first one is born of rockets, of course, building and launching rockets. That's about half the company. And the other part is actually Space Systems Division, headquartered in Long Beach, California. What Space Systems does, which is I'm part of that division, is make satellites, essentially, small satellites. And then we could either use our own launchers at Rocket Lab or have it launched by SpaceX or some other launchers, Firefly, or whoever. So it's a collaborative, sort of a synergistic approach to making satellites and launching them to space, because ultimately that's what you want to do. But in addition to that, the space systems have different business units that provide various components to the satellite itself. One of those business units that I work for is actually called Solaro, or Solaro by Rocket Lab. Solaro has been in business for many years. We're headquartered in Albuquerque, New Mexico, in fact. We are the largest supplier of space-grade solar cells in the world. About 35 to 40% of all satellites that are launched are powered by our PV components, solar panels and solar arrays and so forth. So, and I go into a little more detail on level of power and so forth, but I just want to give you a little bit of background on what Rocket Lab does and who we are and what we do. So I only have 2 slides, but I'm going to spend some time on these because space solar power has been ubiquitous since the 1960s. It's desirable because it's semiconductors, just converting light to electricity. There are no moving parts, no sounds, there's no safety issues. It's a direct conversion of light to electrons, essentially, that generate electricity. So vast majority of all missions, whether they are interplanetary, in low Earth orbit, mid-Earth orbit, like GPS, or geosynchronous orbit, are powered by solar arrays. So if you can see there, we have actually powered a lot of lunar missions, including LRO and LADI and so forth, which are mainly orbital missions. But of course, a lot of missions are planned for the lunar surface, and we go over those in the next slides. But the power levels vary quite a bit. They could be as little as 200 watts to close to 70 kilowatts. In the previous panel, Chris Coker explained what PPE does and so forth. That's one of the largest solar arrays ever built, in fact, and is powered by our solar cells. And of course, the largest solar arrays ever built and flown is the ISS solar arrays. And that's an interesting case because the solar cells that powered that original solar array, 150 kilowatts in fact, was 14% efficient silicon solar cells made by Lockheed Martin years and years ago. You may have heard that recently they were replaced by the rollout solar arrays by Redwire, which uses efficiencies that are more than double of those very old technologies. And so they're being laid over the old solar arrays. Much smaller, but generate actually more power. So space has actually forced the solar cell efficiencies to be improved by quite a bit. It's the only forcing function. For silicon solar cells or solar panels that you have on your roofs, for example, the efficiency is improved a little bit, like from 14% now to close to 18% or so efficiency. Whereas because of requirements for space, which require smallest solar array, lowest mass, because you have to have stowage within the fairing of the rocket. Mass is important. Everybody talks about that. Of course, you have to have lowest mass. That efficiency now is more than double what you have on your rooftops. So under space conditions, the highest efficiency solar cells we make is 34%. Under terrestrial conditions, on the surface of the Earth, it's close to 38% efficiency. Compare that to 15, 16% efficiency that you get. So it's an incredible forcing function, but it's also an enabler. And I go over it. And the enable part is important because if you look at some of the pictures I have down there, one is the Mars Ingenuity helicopter, which is a marvel, right? It's still flying after 50 flights. What you can see, there's a little solar array this big on top that is powering that helicopter. Those are the lightest, most efficient solar cells ever built. And without that kind of technology, that helicopter could not fly because it'd be too heavy, too large. So this is an example of what high efficiency PV can do to enable a critical missions like that, the demonstrator. And of course, when we go back to Mars for sample return, there will be more helicopters, larger, but also using the exact same technology. At least that's the plan. But in addition, so you can see on the right, there's the Earth, and there are all these satellites that are going around it. That's just a small representation of how many satellites are being, right now, today, circling the Earth from different orbits, all of which are powered by PV, by solar panels. Nearly all, or most of which, are high-efficiency solar cells, for example. But you can also see there are missions to the sun, very close to the sun, Parker Solar Probe, missions to Mars, missions to, of course, the moon, but also to asteroid belts and to Venus and to Mercury and everywhere, so, and even to Jupiter and its surrounding environment, other asteroids near Jupiter. And there are plans now to use solar for Saturn. Now, to put things in perspective, Saturn, the sun's intensity is about 1% of what you have here on Earth. So the sun looks this big. But solar still is going to work there. So it's everywhere from, you know, a couple hundred watts to, you know, 35 kilowatts, 70 kilowatts that's used. But today's annual production of all the world is about 1.3 megawatts. Just 4 years ago, that was about 700 kilowatts. You can see how the explosion of you know, business in space, mainly driven by industry, but also by both DoD and NASA and other civil space agencies around the world. We supply mostly to the U.S. customers, you know, from Lockheed Martin to Northrop Grumman to others, but also to Japanese Space Agency, to South Korean Space Agency, to Indian Space Agency, to a lot of Europe, and even South America. So it's everywhere and it's growing. So it's doubled in terms of power requirements and expected to go even higher, especially with the advent of constellations that are planned. And those constellations are both governmental, like Space Development Agency. You may be familiar with that. These are the various tranches of tracking, and for example, and but also commercial, mega constellations. Mega constellation, each one that's planned that are commercial, they use about 2 megawatts each. Now, it just showed you that the current annual delivery from everywhere is about 1.3 megawatts. So you can imagine if some of those constellations hit, which they are supposed to hit maybe later this year, that it creates a bottleneck for solar. A couple of other pictures there I just wanted to show. One is the Mars InSight lander that was covered by dust. We talked about dust before, that it can be a problem. And of course, you know, solar arrays can work forever. I mean, there's literally no, especially with an environment like Mars that has, or moon, that surface of the moon, there's no radiation to degrade it. But when you have dust on it and other environmental factors, that's where the, you know, energy losses occurs. And then you have the CRS mission that was mentioned earlier. That's the Northrop Grumman commercial release supply services. These are the Ultraflex round solar arrays that you can see, and we supply all of those, and they routinely go to the space station, deliver cargo, and so forth. And then there is the OneWeb Gen 1 picture there, which but over 600 satellites on orbit, and we started supplying the solar panels to them just several years ago. And impressively, to the lower right, there is this huge solar array, which is the NASA Lucy mission that we delivered to Lockheed. And the actual solar array was actually produced by Northrop Grumman. We provided the solar panels that go inside it. You can see the scale of that. So solar power can be from CubeSats, just a few, like 50, 60 watts, to really large quantities. So my last slide, I just wanted to summarize the lunar surface mission from the perspective of you know, solar. You're all familiar with the NASA CLPS mission, Commercial Lunar Payload Services. And here are some of the examples of some companies that are servicing that mission. One is Firefly Aerospace with Blue Ghost Lander, Mission 1, which is about 200 watts. We supplied the solar panels to those. And the new one that they award they received from NASA, CS3, which is about, you know, much larger, close to 2 kilowatts. When I talk power right now, I'm just talking about beginning of life power, not end of life power. Then, of course, there's Brookhaven National Lab, which is the Lunar Surface Electromagnetic Night, or Lucy Night. It's only 200 watts, but it sits on the surface of the moon, and it also will use the highest efficiency solar cells ever produced, also the lightest. And lightness for the surface of the moon is really important, the mass, because it costs on average about $1.2 million to take 1 kilogram of mass and put it on the surface of the moon. Compare that to low Earth orbit, which is $10,000. So you can see what the difference there is there. I have other examples of astrobotics and intuitive machines, of course, and iSpace, which is commercial. We supply solar panels to some of those. And there are other missions like Cadre, that's a cooperative autonomous distributed robotic exploration by JPL. We supply a lot of JPL's requirements. And of course, the big one is just NASA Artemis. And I think we talked about the VSAT that Lindsay mentioned. These are vertical solar array technologies. They can be very large, tens of kilowatts, and they could be lots of them. Currently, there's a study phase that Lockheed Martin Astrobotics and Honeybee are selected by NASA to perform. But one concept is the grid, Lunar grid, which is you have these VSATs, solar arrays, just sitting around, and they're connected essentially. And they're off the ground and could be in the South Pole, for example, where the sunlight could be nearly permanent in certain places, and they could share power and move power around because, as was mentioned earlier, unlike nuclear, which can provide day and night power, solar needs the sun. So one way of getting around this is have this lunar grid that could go around and find ways to face the sun at all times, especially in the South Pole, where the tilt allows for that to happen. So that's all I had.
Thank you, Naveen. All right, we're going to open it up for questions from the floor. I've got a couple before we get started. Everybody's touched on the idea of having power on the moon for multiple users and multiple uses. And one of the things that we didn't really talk about is the idea of a grid and being location dependent or location independent. And Lindsay, you mentioned it briefly, that's a longer term plan. I just wanted to ask, from the solar array perspective, from the nuclear perspective, and generally, where do you see that tipping point? When do you see going from individual technology demonstrations, which are what are funded right now, to operational systems in a specific location, to actually having a networked power capabilities? So I will let you guys decide who's answering first. Naveed's nodding the most, so I think I'll start with him. We'll go by the head nod theory of panel management.
Well, it's exactly what I was just talking about, so-called lunar grid, which I think the tipping point is when, right now, it's mostly science and exploration, right? You have rovers planned, you have landers planned, and it's mainly for science and, what we've done, or we want to do, what NASA wants to do with the surface of the moon at the moment. But past that, you're talking about a lot more frequent visits and having astronauts, of course, and at some point maybe permanent habitation. That is the point where you need the grid. You need 24/7, the lunar days and hours of power on the moon. Because once you have astronauts there, you cannot rely on the batteries, because they run out, of course. You need power, either solar or nuclear or whatever that is. But there are ways of using the locations, certain locations on the surface of the moon, again, closer to the poles, where sunlight does exist nearly permanently. And if you have a grid where you have these sort of VSAT solar arrays spaced regularly, and they share power and they move power around, you can manage that. But there are certain places that half the cycle of the moon is in darkness and half is in light. So in the darkness, there are certain regions that solar simply can't be there. But there are ways of going around that, but mostly closer to the poles.
I can't believe you keep passing up the opportunity to say peaks of eternal light, which is the most poetic way to say that, permanently lit.
Permanent light, yeah.
Vince or Lindsay, anything to add? And then I think I'll open it up to the floor.
I guess I can add a little bit. So I kind of see, I had the 3 phases up there for the kind of that start of a power grid is likely would be part of phase alpha. However, it depends. You may have a kind of a micro grid as part of your Artemis base camp. And what's the definition of a grid? Is it a couple sources of power connected to a single input? I think you'll start to get some of that initial small power grid type of stuff towards the end of an Artemis base camp, but it's really not until you get to that phase alpha where you're starting to bring more of that industry in, you're doing more of the ISRU, that you would start to have kind of that power grid put in place. And I think Naveed, with your comment that sometimes it could be challenging with the solar, I think it just points out we've got a diverse panel here as far as you do the photovoltaic, but we've got the fissions, and I think it's a combination of everything that's going to make this successful. So where the solar has gaps, that's where nuclear can kind of pick that up. It gives you that option.
Vince, anything?
Yeah, I just might add that it's important to understand that NASA and the government is going to be the anchor customer for the initial power grid on the moon. And I know we grappled with this in our phase 1 FSP study. Depending on where you're going to put this system, there are environmental factors that can drive the design or certainly affect its efficiency. So the sooner that we know where NASA wants to place Artemis Base Camp, I think that'll maybe drive some additional momentum towards, okay, let's think seriously now about laying out a lunar power grid in that vicinity.
Okay, thanks. Let's go to the audience. I've got way more questions for all of you, but I think it's your turn now. Your microphones are down there. Hello, Jeff Faust. How are you?
Good afternoon. How much synergy is there in reactor design or other technologies between fission surface power and nuclear thermal or nuclear electric propulsion? How much can fission surface power leverage investments in those other technologies, and vice versa?
I'm tempted to take that myself, but I think I'll
go
let
ahead.
it's the similarities are actually greater, as Vince mentioned earlier, between fission surface power and nuclear electric. It's that power conversion technology that's going to be key to making that transition from for fission-based electrical systems in general. Vince, you want to talk anything about reactors, or I think we should keep that pretty high level in this room.
No, I think we keep that high level. The one aspect I would add is the idea of scalability. So it's important that as we design these systems at, let's say, 40 kilowatts, that we are thinking about how to scale them up towards 100 kilowatts or higher, which then gets you into the nuclear electric propulsion arena. So that's the other important factor as we do this early design work.
And that's also important looking forward to Mars, is the ability to put infrastructure there of the scale required to support human aspirations, human scale operations at Mars. So being able to create those scalable systems at the moon is part of that moon to Mars architecture. All right, thanks, Jeff. Really? Nobody has any curiosity out here about this amazing topic that's going to power the entire economy and human exploration on two planetary bodies? There we go. Ron, you need a microphone. Well, you probably don't need a microphone, but you should have one.
I can probably belt this out. So thank you for all of the discussion. Area of interest is, once you have a microgrid in place, what are the thoughts about transferring the power from the sources to the sinks? Is that the thinking along the lines of beaming or hardwire connectivity?
I'm going to add on to that because that actually is part of a question I wanted to ask too. Taking moderator privilege here is also about interoperability, because it's not going to be one user, it's going to be multiple ultimately. So power to the grid, power to the user,
Power to the panel.
power to the panel. Naveed, you're really good at nodding. I'm going to let Vince go first though.
Well, you may have seen some concepts already of actually wireless power transfers. You've seen that with the Lunar grid, for example. Power beaming, of course, is now gaining a lot more traction. Demonstrations have happened already on orbit. But there's good old wires as well. So there are various ways of doing that. I don't think we've settled on anything yet. It all depends on, a lot of logistics and where the base is and everything else, but there are various ways of handling that for sure.
I think that's the other element that's not on Vince's chart about things that need to be matured.
Yeah.
No, that's a really good point, Lisa. And I would add one more element to that, and that is the standardization. So who is going to decide what the plug-in interface looks like, right? A good analogy is what's happening today in terrestrial electrical vehicles. You've got Tesla system and you've got everybody else. So you've got two standards, and if you're driving an electric vehicle and the red light is flashing and you're trying to find a station, that becomes a real world issue for you. So we need to give some thought to the standardization of these interfaces sooner rather than later.
I just happened to learn the other day that Porsche has their own standard. I was looking for something on a map, and there was a Porsche charging station, and I then went down that rabbit hole. So yeah, it's definitely, we need to enable multiple users, but are we standardizing, or is it bring your own adapter land on the moon? Lindsay, thoughts?
Yeah, I just want to maybe put a plug in there for something that Glenn is working on. It's called Aspire. It's a small microgrid that's going to kind of, it's intended to simulate an Artemis base camp, that power infrastructure, and so that might be a good opportunity to check out the interfaces, the portability, things like that. It's a program. It's in various. I think there are 4 phases altogether. They're looking at finishing up the first phase. They're looking at a 3 kilovolt AC power transfer, but it could certainly be something. I think that would be a good application of that program.
And that's part of Glenn Research Center's testing capabilities too, right?
Yeah.
That's a big surge here at the center. So
Very quick follow-up.
there's no one standing at the mics. You can talk, Ron.
Keep the conversation going. In that context, Lindsay, would it then be the Aspire be available to the community at large as a test bed including that?
I believe that's the intent. I'm not close in on the details of it, but from some overview charts I read, it's supposed to benefit everybody. So I would see that.
I saw some people standing up.
Yeah.
They sat back down. They're back up again. All right.
Yeah, for the fission people, what's the expected lifetime of a surface nuclear system? What's the main technical obstacle to extend the lifetime, and what are your thoughts on how we would decommission a nuclear system on the moon?
Sure. So right now the design requirement that we're targeting is 10-year life. And I would say that the reactor, once it's up and running, wants to just keep cranking out. So the limiting factor on the reactor is just how much fuel you put in it. So we're more worried about the power conversion system and the not so much the power electronics, but really anything that's got moving parts in it. Can you engineer that and test it out reliably to last at least 10 years, if not longer?
And I'm going to just throw out that hardy perennial of lunar dust. With making sure that we have mechanisms that deploy and making sure that we have connections to our burgeoning grid that we're developing here on the panel, that those all work in the lunar environment as well.
One question, Jeremy Blalock, Dynetics. So one thing that we worked on was the interoperability. So the fission surface power, the solar surface power, all these things are great and aspirational. But when it comes down to, the brass tacks, is getting that to the surface. So I would encourage NASA for all the CLIPS landers and HLS landers to look at interoperability of how these large, 20 metric ton payload landers or greater can, carry these experiments down to the surface with them. And for other landers such as CLIPS that remain on the surface, those are assets that we can utilize. So maybe, as part, if they have excess payload, maybe they can carry down and be a base station for some of these experiments. We're always looking for launches, and how to get something to the surface is very, very expensive, in the hundreds to sometimes $1 billion to get something on the surface of that size. So I would say, for NASA, please encourage the interoperability. Thanks.
All right, we have just a couple minutes left. All right, Jim, are we by the popcorn theory of technical sessions?
If there's nothing else.
All right, well, let's thank our extraordinary panelists for their time.